Well, thank you very much, Pierre, for doing that. And my name's Jeff Brumfield. I'm a reporter with National Public Radio who covered this eruption when it occurred and shortly thereafter. And I should start out by saying that I'm afraid, despite taking great pride in pronouncing things correctly on the radio, I've already been informed by Dr. Floyd's immediate relatives that I am not pronouncing it right, and I'm not sure I can, but I'm going to give it my best shot, guys. Tonga-Hunga, Haapai. So, middling. Okay, but we're going to live with it, and perhaps refer to it. David said we could call it the Hunga eruption or the Tonga-Hunga eruption. We'll kind of fudge it, but I appreciate your patience. Shane probably knows how to pronounce it properly.
Yeah, we call it Hunga because the whole volcano is Hunga. Hunga Haapai was one of the islands, and Hunga Tonga was the other one that was on the surface. So the whole volcano, the big submarine edifice, we call Hunga.
Hunga. All right, great. So with that, I am going to introduce our panelists here. So we have Shane Cronin from the University of Auckland, who was one of the very first international volcanologists to arrive, I'm told, after this eruption occurred. To the left of him, we have Stephanie Donner from the Federal Institute for Geosciences and Natural Resources in Germany, who, as I understand it, you were involved with looking at the IMS data and kind of analyzing. We can talk more about that in a sec. To her left, we have Peggy Helveg from the Seismological Society of America.
Yep.
And then, yeah, I'm sorry, I shouldn't be phrasing these as questions. These are who these people are. David needs no introduction because Pierre introduced him, of course. And then is Sarah Barsotti with us virtually? Can she speak? One moment, okay. So she is coordinator for volcanic hazards and leader of the State Volcano Observatory team at the Icelandic Meteorological Office. Oh yes, there, I can see her. Hello. Nice to see you.
Hello, everyone.
Oh, there you go. All right, great. We gotcha. So I thought that we might start. I feel like we have a sort of geographically diverse panel and a panel of diverse backgrounds and sort of approaches. And I thought maybe the first thing to talk about would just be kind of what your immediate response was when you saw this eruption, how you saw it or experienced it, and sort of the first questions that came to your mind. And we can, I know some of you probably have prepared remarks. You could segue into that as well. So maybe, Shane, we could start with you.
Okay, so I'm an earth scientist or a geologist, and I've worked a lot on Tongan volcanoes, and I've actually spent quite a bit of time camping on this volcano in 2015 and mapping the bathymetry of the volcano. So during the eruption, I was actually speaking with Taniela Kula, the head of the Geosciences Division in Tonga, and then our connection was cut as the international data cables were cut off from Tonga, and then for 2 days we heard virtually nothing from the Kingdom of Tonga. So my experiences during the event were sitting on my computer trying to find out information about it. I didn't hear the sounds, although a lot of my colleagues did in Auckland. It was 2,000 kilometers away, because I was too busy trying to find out what was going on as my phone was cut off from Taniela.
And so what was sort of the first question you had about it? Do you remember sort of their first?
Wasn't terribly surprised because we'd published a paper a few years before describing the small-scale eruptions of 2014 and 2015 and the potential for this volcano to produce larger caldera-forming eruptions. And then subsequently, I've spent a lot of time in Tonga researching this event, and I guess we have more questions than answers. We're starting to get a feel for what the driving mechanisms of this eruption were, and we are adapting and stretching the kind of volcano terminology, but also the volcano theory to fit it. So for example, one of the observations that David was pointing out was this depressurization surrounding the volcano during the initial stages. And that's fairly easy to understand when we start thinking about the way in which this plume was formed. So we've been applying volcanic models to the plume, and they are not working. The plume was not a plume driven by the ejection of volcanic material from a conduit, but it was a plume driven by a thermal updraft of low density material, mainly water, and that created the conditions not only for rapid rise, but for rapid expansion of the plume. And that rapid expansion, the so-called mushroom cloud effect, was pulling in air at a rate we've never seen before, except for the very largest eruptions.
Stephanie, do you want to go next?
Yes, sure. So I think our first reaction as a working group from the German National Data Center was similar to everyone else. It was breathtaking, and we thought immediately that this could be a benchmark data set in the framework of the CTBTO for a multi-technology analysis. Just the vast energy coupled in all three media from the three waveform technologies for the CTBT. So it is a perfect natural test case to investigate and to further develop the methods we have at hand.
Calibration event.
Yes. So on the one side, we were interested on the multi-technology analysis, and on the other side, we were curious about how many details we could get from the source process of the main eruption phase in the morning of the 15th of January. And we were surprised how many details we could determine, especially when we compare source time functions from the different waveform technologies in comparison to each other.
Mm-hmm.
Yeah.
Sarah, I'm going to turn to you online there. What about you? You're in Iceland where the volcanoes are even harder to pronounce. Sorry.
Hi, everyone. Can you hear me well?
Yes, we can hear you pretty well.
Very good, very good. So, hi, everyone. So I guess my words here maybe are a little bit shifted from the focus regarding purely scientific questions and topics, and it is more related to an hazard assessment and emergency response perspective. And so then why is Tonga-Hunga eruption relevant in this sense? We heard that a wide range of remote sensing data and satellite data were accessible pretty soon, since the onset of the eruption on the 15th of January. However, it is worth saying that very limited ground data, if known, were available in near real time. So as we just heard, there were disruptions to the internet communications that in the end resulted in the impossibility for the local volcano observatory, the Tonga Geological Services, to provide updates or issue bulletin or share information on the situation. And indeed, it took hours before remote sensing information was able to shed some light on the impacts, on the damages caused by the eruption itself and the resultant tsunami. And all this was not validated by those on the ground until days later. So in a way, there was a temporal gap during which it was very difficult to assess the impact of the eruption, the damages, the entity of that event, even though, as we heard, the eruption was measured and observed throughout the whole world. So I guess the Tonga eruption still demonstrates that it is still challenging to respond to eruptions when limited ground data is available, and it is a very good test case to discuss on how much this difficulty is even amplified when we start talking about international response to volcano emergencies.
That's really interesting, and I think we should come back to that. But sort of continuing with first impressions here, we'll go down to Peggy there.
Yes, so coming from the earthquake monitoring world, my reaction was, this is big. Big is always bad. And of course, like everybody else, I didn't find out how bad it was really until quite a bit later. I also thought of the CTBTO and the data, but as a normal university person, I didn't have any access to it. So there wasn't really anything I could do in that sense. But as the president of the Seismological Society, which was currently organizing a meeting for a few months later, I said, we can make a venue where information on this eruption, whatever we find out in the next few months, can easily be exchanged. And so I made sure that we would have a session that people would be allowed to submit abstracts until fairly late in the game, and that we started the process of preparing a special section in one of the SSA journals for people to submit to.
It's interesting just hearing the sort of diversity of things that were happening right after this eruption to sort of prepare the scientific community and respond to what was going on. David, you kind of gave a sense of your first response, but you know, I'll ask you again kind of to go over it and what your first sort of questions were.
Yeah, my experience was a little bit different and interesting, I think. So we actually had a new baby, and my wife and I were up like at 4 a.m. with the baby, and we just put him down, and then we were laying in bed, and I heard these weird sounds outside, and I thought it was like, just to be honest, like somebody like breaking into our garage, or like just maybe military activity. But I just went to bed, right? And I was tired. And then like I woke up in the morning and checked the news and like saw that this eruption occurred. And then like a colleague said like, oh, people in Alaska are reporting that they heard the eruption in Tonga. And I was like, no way. I was like, this is my career. I study like volcano acoustics, right? Like, I was like, that's not possible. And I was like, oh wait, I heard some stuff last night. And then I went and actually checked our data, IMS data from like our backyard, and I was like, wow, that timing, did some basic math and the timing works out, and I was like, oh, this is incredible. And I think right there it hit me that like, because I saw in the news that there was eruption, but there was really no sense of scale, and I think that kind of immediately got to me that like this was really something big and unique.
Yeah, are there any recordings of it anywhere? Did anyone capture it?
Yeah, I know like a lot of, well, I mean, we have a lot of geophysical recordings, but like a lot of just like cameras and microphones that were recording captured it.
Yeah, there are a lot of local recordings of it in Tongans on their cell phones.
Yeah.
What I found remarkable was the sound was like, as you say, military type of sounds. I've seen shockwave type phenomena or explosions at many volcanoes, and you have these low booms, and sometimes you feel it on your body. But these were sharp reports and horrifying. So a lot of the children and actually a lot of the people, a lot of the adults in Tonga are still terrified of both of the ocean, but also of any loud noises.
So when did you actually make it into Tonga, and what did you see when you got there?
So I arrived in Tonga at the beginning of March, right in the middle of it was COVID lockdown. So my first impression was there was very little volcanic ash or tephra. I expected this enormous eruption. First of all, we expected the enormous eruption to have generated a lot of fatalities, especially once we knew the tsunami was so large, and we were surprised that there weren't. But I was very surprised as a geologist to see how little ash there was. And then I was surprised at how large the tsunami waves were. And subsequently, I think that's led this search to understand the mechanisms of the eruption. There's something quite different to terrestrial eruptions, and the normal models we use for terrestrial eruptions are not working. And so I think this is a really good opportunity to sort of bring together some geophysical observations with these very unusual geological observations of an event of this magnitude. So when we see an eruption column that goes above 35 kilometers into the atmosphere, and there are reports of this one reaching higher than that, we expect to see huge deposits, and all our models are based on that. When we see tiny little volcanic ash layers and very little deposit material on land, and we would see that in a geological context when we're trying to do a hazard assessment of an area, we would ignore it. We would think this is a small event and move on. So how many others of this type have we ignored in our geological assessments of the region and other regions with submarine volcanoes of the like?
Stephanie, I was wondering, you mentioned earlier that this was a particularly interesting event for the CTBTO network because it was recorded so strongly, kind of on all channels, on all. What was your takeaway from that, or what did you learn, I guess, from the event and how it was picked up by the network?
With respect to the IMS data and our methods?
Mm-hmm.
Okay. Well, the main key message is, I think that the IMS is very well suited to fulfill its duties from the CTBT. So we could detect, locate the event, and we could also determine the source mechanism, discriminate it from an earthquake. We could even discriminate it from a normal explosion. I mean, a pure explosion is something very constrained in time and space. But here we had the constraint in space, but not in time. It was very long. So we could even discriminate this very well. IAM is ready to do so. Even so, it is not a nuclear explosion. We also tested the atmospheric transport modeling, which is meant to discriminate between a pure explosion or a nuclear explosion to track the radioactive particles in the atmosphere. Of course, we measured nothing, but we performed back tracing to see if it would have been a nuclear explosion, would we be able to measure the particles radiated by an event of this strength? And the answer is yes, we could. So basically, we are fine. Duties are covered. But we could even do better. So this was an event which was neither an earthquake nor an explosion, and it was neither onshore nor offshore. So we had energy leaking in all three media, into the atmosphere, into the ocean, and into the solid Earth. And from analyzing the timeline of the source processes, we could even distinguish at which time energy was leaking in which media. And we learned that we could even do better, fulfill our duties from the treaty, if we have better models for this interaction, for the coupling of the energy, for the leaking of the energy into the different media. So this was one key message. And the other key message was concerning the strength of the event. Analyzing the DPRK tests, we usually determine the body wave magnitude and then use a body wave yield relation to get an estimate on the yield. Of course, this didn't work here because we couldn't see the P phase, which is necessary for the body wave magnitude. And though we have first approaches to determine the strength of an event also from infrasound and hydroacoustic data, we need to spend more efforts into the science there to get good strength estimations from all three technologies. And I think the holy grail will be a coupled strength estimate where we include the data of all three waveform technologies.
Do you think, the data from this event, will this help you sort of build the cross-linking, I guess, connect the models, as it were, more closely?
Yes, I think so.
Yeah.
This is just from its pure strength and from the vast amount of data we got of this event, I think we have plenty of possibilities to exactly do this science based on this data set. It's a ideal natural test case to do so.
Mm-hmm. Sarah, I wanted to, as I said, come back to this initial point you made, which is like, we have our scientists up here on stage who are pointing out that, very quickly they had an enormous amount of data on this eruption, and yet for emergency response, you didn't have what you needed for the international community in a way. In fact, things were probably made worse because other kinds of data, like the undersea cables, were cut. It was hard to communicate. What lessons, just sort of returning to that topic, What, I guess, we live in this era where we can get all this great scientific data. Can it help improve the response even when you're in the dark because you can't get through? What did you learn? Oh, I think they need to unmute you. Hold on, sorry. It looks like it looks like it's a great answer. We just need to hear it.
I was going to start. Sorry for that. Well, again, at the time of the eruption, the European Natural Hazard Scientific Partnership, which is called Aristotle, was activated by the ERCC, which is the Emergency Response Coordination Center. That is, I don't know if you're familiar with that, it is the heart of the civil protection mechanism in Europe. And it coordinates between civil protection and humanitarian aid operations. So Aristotle was activated in order to provide, within a very short time period, it is most of the time 3 hours, an expert evaluation and an assessment on the ongoing event in order to support their response, in order to help them evaluating what was the situation, impact, consequences, and even evolution scenarios. So as I was saying, there were all sorts of information available, but still what was the main theme was the still large uncertainty about the quality of information that we could provide to them. Again, on one side, the Volcano Observatory was doing, again, before all the cut of the communication, all their ground-based observations and disseminating all this information. On the other side, the Darwin WAC, they were of course doing all their, they were playing their role as soon as the eruption started in order to distribute information, in order to maintain the area safe for what concerned the aviation. But I think there are two main things, two main questions that still raise in light of the event. And maybe it is worth to put some emphasis in terms of where we can still improve, how we can still plan next time to do better. And I believe there are still two main areas where we might think of spent energies. One is, of course, the intergovernmental cooperation, and the other one is the data distribution and accessibility policy. That in a way, how we can move through these two lanes in order to improve the disaster risk management and mitigation. We know in the world currently the situation about volcano observatories, they're still poorly connected between them, and there is a general lack of coordination. And we can imagine how much better the response would have been structured if there would be a kind of a better structure or organized entity where all the volcano observatories would just belong to. For example, just in terms of developing standards, developing good or best practices and guidelines, and even more, for example, designing or customizing scientific and monitoring support during emergencies. There have been initiatives that so far have been put forward. One of those is what the IAVSEI, the International Association of Volcanology and Chemistry of the Earth's Interior, is doing since few years in order to reinforce the World Organization of Volcano Observatories, for example. But I believe what is needed at this point, we have all bunches of data, but I guess we need the voice of the Volcano Observatory to be heard. So I think what is needed is more a recognition at higher level, like the UN, of the need of representatives from volcano observatories as a body, so that they can really say and speak loud about which are the needs and the way to move all this forward. And the UN Early Warning for All initiative that was launched in March 2022 is that kind of initiative, where volcanic eruptions and volcanic hazards have to be included. And I guess it is through this kind of initiative or actions that the Volcano Observatories community can be recognized as an entity and eventually an interlocutor to discuss with. And of course, the CTBTO monitoring capability should be listed within those resources that at international level can strengthen the capability to respond to volcano emergencies and eventually provide support in managing crises like that.
Great.
May I follow up on that point?
Absolutely,
Yeah.
sure.
I just want to highlight that Tonga is a country with around 100,000 people and around 12 active volcanoes. The highest qualified person in any way, shape or form in terms of seismology or volcanology has a master's degree. So coordination is one thing. The other thing that's really needed in places like Tonga or Vanuatu, Fiji, in these remote Pacific islands is huge amounts of technical assistance so that they could actually benefit from being within a coordinated network. There is a huge lack of human capability as well as a lack of on-the-ground data. And one of the things that challenged us throughout this whole event is the lack of any local seismic information, for example, but also the extreme lack of knowledge on the ground or in terms of an observatory that can pass on life safety information to the public.
Yeah, I remember actually speaking to you around the time of the eruption, I think following up a few months later, and you did point out at that time that there was just this incredible lack of local instrumentation. Given how active the region is, the instrumentation was very sparse and the expertise were very sparse. I mean, do you have any bright ideas about how that could be rectified? Or?
Well, yeah, this is where international organizations really need to step up a little bit and devise ways and means of assisting countries that aren't able to maintain over generations this in-house capability. So obviously expanding the range of networks and expanding technologies that can be used in remote settings and in more difficult to operate settings will help maintain observations across the world and will help countries like Tonga.
I'm going to open it up to questions from the audience in a minute. I've been told that there is I'm going to open it up now. I've been told there's an online app where you can enter questions, and I have an iPad in front of me where they may or may not appear because I haven't used it before. We also have microphones up here, so if you want to start entering questions, lining up, feel free. While you're doing that, I might ask Peggy, I mean, what was the, sort of that first round of scientific results? What did you see?
So we downloaded some of our data to look at it, and what was really very exciting was to see the tsunami appear in lots of different places where we didn't expect the tsunami. On the one hand, the tsunami was visible as a sound wave in the air that coupled into our seismometers. It was visible essentially as the water coming close to the coast where we had near coastal stations. The complexity of the tsunami wave that affected our seismometers was, as has been pointed out by David and others, very complex. From a seismological point of view, I have to say there's another topic that hasn't been covered very much here, which is the tsunami forecast from the eruption. And the reason is that the tsunami warning centers, at least those run by the US, have mostly concentrated since 2004 on tsunami and improved their capabilities regarding tsunamis from earthquakes. And that they didn't know that there was really something that they needed to worry about until the tsunami wave crossed the first dart, which I think is in front of the Australian coast. And so then they said, oh my God, there's this big thing. We better tell everybody there's going to be a tsunami. And then it went around the world. I think one of the lessons from the tsunami in 2004 was also you need to have your communication channels in place well before you need to communicate the alerts. And it's not clear to me, because it wasn't my job anymore, that it worked as well as it could have worked in the case of the eruption, since it was something very new in our recent experience.
Yeah, it's fair to say that tsunami modelers didn't regard volcanoes as being able to produce tele-tsunamis, so to speak. One of the remarkable things for me was the amount of education, though, that has gone into tsunami awareness in association with the expansion of the warning systems. The awareness in the communities is very high. And so there was a tsunami warning issued in Tonga the day before the event. It was withdrawn because although there were still regular waves of less than 20 centimetre on the tsunami gauge, on the tidal gauge, that was below the threshold. So there was no active warning. But as soon as the local people saw that the eruption was getting bigger and the first few changes in the wave pattern, particularly withdrawal of the waves, everybody evacuated. And so there was only 3 fatalities.
I understand there were 2 on the coast of South America also, and it's not clear to me why. I don't remember that.
Yeah, I'm not familiar with I know the story, but I'm not sure why. But I mean, the tsunami hit New Zealand, and we didn't have a warning in place, and boats were damaged, and the same thing was the situation in Fiji. But the local awareness and education meant.
That's really wonderful. They've been some places in the U.S. have also been very good about it.
Yeah.
So the other thing that I found really amazing was that normally you have a tsunami and it stays in its ocean basin, probably because Tonga is so far south, the southern oceans are more open, so it did go into the Atlantic and the Indian Ocean, but it also crossed into the Mediterranean, which is sort of a closed ocean, more or less. But I think mainly because of the land wave and the other atmospheric phenomena associated with it.
I'm just looking at the iPad. I'm not sure. I don't see any questions here, and I don't know if that's. Do you want to take a quick look?
Yes. Does this work? Yeah. So one question for Shane, since he has been possibly one of the first to go there and survey after this eruption. And since the study of the mechanisms that generated the tsunami, I think, will still be a topic of debate, and there will be many insights to be made. Do you have anything that you can tell us about how you saw the bathymetry changed? Is there anything that surprised you?
Absolutely. So the mechanisms for tsunami generation on volcanoes, we generally think of the most efficient one is a submarine flank collapse. And that was our initial model for the eruption before we went there and carried out the bathymetry measurements. So prior to the eruption, the summit of the volcano had 2 small islands and a relatively flat topped volcano around 6 kilometer diameter with the deepest part around 150 meters. After the eruption, the rim, if you like, of the volcano was fairly similar to previously, but there was a large hole created 4 kilometers wide and around 1 kilometer deep. Part of it's filled in the base. And also the whole southern portion of the volcano has dropped by about between 30 and 50 meters. So there's been a substantive change to the surface of the volcano and the shape of the volcano. If that could have been a tsunami cause as well, so tsunami generation in the absence of our submarine gravity flows, we have a mechanism of so-called caldera collapse, where we have the central portion of the volcano collapsing in on itself, water drawing in. We have situations also when you have an eruption plume or eruption column, and when that stops, that excludes the water to begin with, and when it stops, the water comes in. A third situation is that you have surface explosions through the water and the atmosphere, and we certainly saw 2 surface explosions, both of which were followed in regular time by a tsunami arriving on the western coast of Tonga-Tapu. So we did see 2 explosion-generated tsunami. The largest one that had a 20-meter run-up on the main islands of Tonga, we don't know exactly what caused it. It could have been a combination of this caldera collapse and a third mechanism where you actually collapse material from the eruption column into the water. Either collapse or you jet material into the water. So we're at the moment debating on the relative contributions of those different means of creating a tsunami. My money's on the jetting of the pyroclastics concentrically around the edifice, coupled with the caldera collapsing.
I mean, again, feel free to step up to a microphone or enter a question in our online. I am a journalist and thus perfectly happy to keep asking the panel questions. Oh, do we have another one? Okay, go ahead, sir.
Thank you. We heard before in David's talk a comparison between this eruption and the Krakatau, I'm hoping I'm pronouncing it well, eruption like 150 years earlier or so. Did we learn in hindsight of 150 years with all this new data, measurements and analysis, new things, do we understand things now differently about the Krakatau eruption than we did before this Hunga eruption?
Yeah, I can start with that. I think, one of the things we talked about with this eruption in particular, that it was a really complex eruption, and I'm not like a complete expert for sure on the Krakatau eruption, but I think for most volcanic eruptions we have a basic model and understanding, but the Hunga eruption was just, in my mind, incredibly complex and like eye-opening, and so this is for a number of reasons, but just the location where it's like shallow submarine, and then you have a large subaerial component, and it was so explosive when we kind of didn't expect it to be so explosive. So I think that we still have a lot to learn about this eruption. I would say from the waves produced and some of the atmospheric effects and things like that, I think we have a much better understanding now than we did 140 years ago. But I think this eruption in particular was pretty eye-opening to the volcanological community of like what's possible, and we're still kind of trying to figure that aspect out.
Several of my colleagues who work on Krakatau have had a lot of aha moments. So I believe there's a lot of similarities that are being drawn. And we're also looking at other caldera systems around the world. I was in Italy most of last week looking at some caldera systems with very unusual deposits around them. And we're starting to think, okay, these kinds of events may have been present in the geological past and we just haven't seen them.
So in the seismological record, we have always thought of big earthquakes as being simple big earthquakes, but the Kaikoura earthquake, which I think had rupture on 17 different faults, it was a 7.9, sort of like the same size as Turkey, but it ruptured on 17 different faults, is now that we have good information from nearby high-quality stations, which we didn't have for Krakatau, we may find out that volcanoes are all more complex than we thought too.
Sarah, did you want to weigh in at all?
Maybe just one point. What I think is what Shane was saying, of course, the aspect that from the ground observation, eventually there was such a thin remaining of tephra and how much we often tend to connect big signal to big eruption and big consequences, right? I think it is in this sense also a very important case to keep learning. I agree even with Peggy. I think we start to have a kind of draw our ideas about volcanoes, but there is still a lot to learn. And again, moving to the hazardous aspects, right? We could have been imagined that given that amount of huge and very wide impact in terms of, not impact, protection of the eruption, that even the impact was huge. But apparently this was not the case, and as we heard, eventually, even fatalities was really, really low, very, very low toll eventually. So I think there is plenty of space even to keep learning about volcanic eruptions and volcanic hazards.
I would like to add there's something as well, also connecting what,
Sure.
What Shane said. You described about your interpretation of what the eruption of the collapse. This is exactly what we see in the waveform data as well. So inverted seismic waveforms for the so-called source time function, which is basically a timeline of the details of the processes. And this is a pure source signal without any effects of path and side effects. And what we see is a huge, vast explosion, and it seems to be that it was mainly a vertical single force, so directly jumping up. And there's a smaller second explosion 2 minutes later, and 4 minutes after the main explosion, we see a signal with the same strength like the explosion, just with the opposite sign. So it blows up and falls down vertically, almost vertically.
Wow.
So that fits very nicely with the bathymetry data, and I think this is the reason why this event is such a beautiful test case, because we can learn a lot of looking at each single technique, but we learn more if we combine everything. Not only waveform techniques, but also bathymetry and probably also geology and stuff.
But Shane was pointing out that we don't have any local data. And teleseismic data loses all of the high frequency information that you get when you have local stations, which high frequency information describes the complexity of what actually happened.
Yeah, it would be really nice to have some closer data. The closest station I'm aware of is a borehole station and a surface station in Fiji, 850 kilometers away. And Mi Ishihara and her colleagues from Japan have been working on the comparison between the surface and subsurface signals, and so we're getting some good timing information. But one of the mysteries we have is we have this big caldera, and we very rarely have seen a caldera forming during an eruption. And if so, the calderas forming have been the ones that usually sink slowly, not ones like this. We don't really know when that happened. Possibly it happened at the initial time of the big explosion. But and possibly it happened at the time of the large tsunami, which was around 45 minutes after the big explosion. Or it could have happened stepwise ways over the next few weeks. So it would be really important for us to know that kind of thing without having to go around with some circular reasoning.
Actually, I mean, that leads to a question I had for you, which was, I mean, can you just give the very thumbnail sketch of what we do know about what happened? You know, I think that we talked about it maybe a year ago, but I wonder if the picture's changed at all.
Yeah, since a year ago, I think the thinking has changed quite a lot, actually. So to generate this eruption, roughly 9 to 10 cubic kilometers of magma was erupted. We know that around 1/10 of that went up into the plume. Most of the plume was water vapor or steam, which is what's created its very unusual shape and spread dimension. So the bulk of the eruption material went sideways down the flanks of the volcano and traveled up to 90 kilometers or longer away from the volcano as submarine gravity flows. The bulk of that magma that was erupted was blasted to very tiny pieces, so what we call fine ash, mainly pieces that are 64 microns in size or less. And that implies an enormous amount of mechanical energy to break that magma apart. The magma that was erupted was an andesite, sort of what we call an intermediate volcanic composition, and it was erupted at high temperature at low viscosity. So what was driving that eruption was not the magma itself and its ability to trap gases, because it was very poor at being able to trap gases with its internal properties. In fact, what drove it was a very, very efficient interaction of that magma with water, probably through the ring fault system of the caldera and through the fractures in the volcano. So it's, I think for me, a fundamental importance to find out when that caldera motion started to happen, and try to delve through the expertise of people like yourselves, through the seismic signals, through the infrasound signals, just when different types of processes happened in order to create the dynamics. But for us, it's a very different eruption than what we thought it was a year ago. We were thinking of using so-called Plinian eruption models, which are driven by large amounts of magma, expanding magma, magmatic foam out of a conduit. That's the only way we usually generate such high columns. In this case, the high column is mainly water, as we've seen. One of the other things we've discovered is that eruption should have produced more sulfur dioxide than Pinatubo. From the volume of magma erupted, from the sulfur concentration of the magma initially and what it was at the end, we know it should have produced more than 25 teragrams of sulfur dioxide. We measured, or Simon Kahn particularly, measured between 0.4 and 0.5 teragrams of, so where did all the sulfur go? Well, the sulfur went into water, and that sulfur went into water at the initial point of fragmentation between the magma and the water, and so that then becomes sulfur SO4, or it went below water. So it's a very unusual eruption. It's totally changing the way we think about how we make so-called big eruptions. Yeah.
So I have a question online here for Sarah. Working in Iceland, a very active volcanic island, as we all know, is there any lessons that you've learned from the Hunga eruption that are going to be useful going forward?
I guess that's a difficult question, by the way. I think in Iceland we have, compared to what Shane was saying, a pretty well-monitored volcanoes overall, both in terms of geophysical monitoring, geochemical monitoring. So I guess there is maybe not a direct way of comparing the events. What I think, though, is relevant is even in this case we have one of those eruptions for which we can say there was a before and an after. That's the same as it was for the Eyjafjallajökull eruption in 2010. There was a before and an after. Are those kind of, how to say, milestones in the history of volcanology where, again, the whole community will keep learning and will make, again, a kind of, path that marks, in a way, the history. The other thing that maybe it is still worth saying is, and it is a little bit linked to all this discussion, we have to keep in mind that still about 45% of the volcanoes around the world are still either unmonitored or not monitored at all. So what Shane was saying, again, the importance of still having these local networks that are making a difference in putting all the elements, all the pieces of the puzzle together that would allow eventually to draw and understand and in a way even the tangling the complexity of the process that we are trying to understand. And once more, of course, here we're talking about the local networks, but on the other side, again, how much which is the power, I mean, which could be really the CTBTO be seen as a resources in filling the gaps that apparently are still, even though 2023 now, are still something that we are experiencing, how much the CTBTO network or monitoring capabilities can help the volcanological community of filling the gap on how our volcanoes are monitored.
Another question from, go ahead.
Yes, it's actually something to add on to what Sarah just said. The CTBTO hydroacoustic monitoring network is, for example, very suitable for listening to volcanoes that are underwater and very remote. So difficult to monitor because they may not have a surface expression. We have very good examples of that. And because there might not be local seismometers or regional seismometers nearby. And so I just wanted to make that point to add on to Sarah's comment.
Thank you. Thank you, Mario.
Yeah, and I'll just briefly add, we're actually at the Alaska Volcano Observatory using some hydroacoustic data from the IMS to help monitor volcanoes in the northern Marianas that are undersea. And that's really sometimes the only instruments that pick it up. So.
Well, I have one more sort of science question, and then I think we can sort of start to wrap up. And it's for you, David. I am curious, your best guess as to why you could hear it in Fairbanks.
Yeah, I think my current understanding, or like what we think happened, is it's not that there was an acoustic wave at the source that propagated 10,000 kilometers out, but it's related to this really high amplitude, lower frequency wave, and then as it gets close to you at some level, that this wave energy kind of like non-linearly propagates into the higher frequencies. So I think like there's some theory and like estimates of like why that occurs, but I think there's still an open question of why in some places like Alaska or Central Europe, it's heard extensively in New Zealand and other places, do people hear it and not in other places? So yeah, there's I think some ideas on like how, but it doesn't necessarily mean we can model it or we can like fully understand it. Like
so sort of this very, very powerful low frequency wave is pushing some sort of nonlinear high frequency sound waves.
Yeah, I'm not saying everyone would agree with that interpretation, but that's I think our current thinking. Anyone
on the panel want to start a fight?
Sounds like a logical thing. Is it anything to do with the water-land interface?
We thought that it might be something like that, but I'm in interior Alaska, and people have heard it in Central Europe, so it doesn't seem to be any like geographic aspect that we can see yet.
It's not the hills either, breaking up the waves and making them.
I don't know. I don't think so, because of people did hear it along like the coastline. People hear it like next to mountains. It seems like to be kind of all over the place.
Interesting. Well, I think we have about 8 minutes left, and I have no problem. It's been a long day for everyone, and I'm sure we're all the heat of the day is passing, so we can. Oh, we have 2 more people in the room. Oh my gosh, I'm so sorry. Okay, let's get to those questions. I'm waiting. Go ahead. Sorry, I was expecting people to line up. I apologize. I wasn't looking for hands. Go ahead.
Backtracking to the Krakatau question, legacy data has been a kind of important topic lately, and I noticed on your talk, David, that you had the barometric signals from this recent Hunga and as well as Krakatau. Is that an image from the recording, or is that digitized data? And then kind of a second part, if there were digitized data, would you see a benefit to being able to do analysis on that and kind of compare how the sound acoustic waves had propagated at that time versus the more recent Hunga eruption?
Yeah, that's a good question. So we did some basic digitization of some of those old records, and I think, I know other people had done it before. I'm not saying we did it as comprehensively as like, a lot of like a historical nuclear test digitization happens. So I think that, yes, it's been done. There probably is more you could do. I think one of the things we looked at a little bit and you could do more is looking at the instrument responses and how there are some models of those instruments and how they responded, but I think there's probably still some open questions on like fully understanding that. So, yeah.
All right. Second question, go ahead. Or more, if you have more.
Very much. Do we have an idea of the number of active underwater volcanoes which could produce an eruption like the one of the Tonga-Hunga of Krakatau volcano?
Yeah, when we teach our first year students about volcanoes, we show a map and point out that the bulk of them are underneath the waves, and so there are a huge number of submarine volcanoes. So currently, based out of New Zealand and Australia and the USA, there's a lot of efforts going into trying to identify other volcanoes in that kind of sweet spot zone. So we know the dynamics of deep submarine volcanoes, and they can be explosive or submarine explosive, and they generally produce floating rafts of pumice, and that's the major consequence of them. It's just the shallow ones, once you get 150, 200 meters below the ocean surface, that it starts to be a concern. So there's a fair effort underway to try and identify where these shallowish submarine volcanoes might be. What their eruption histories may be is almost impossible to determine because almost none of them been well mapped. So in October last year, when we were remapping the Hunga caldera just to see if there's been any subsequent change, we actually surveyed a couple of other volcanoes nearby that we identified in this sort of first pass in that region. And there's definitely one 20 kilometers north of Hunga, which looks exactly like what Hunga looked like in 2015. Ring fault system, an expanded system, small eruptions in historical time around the edge. So that would be the one I'd put my money on next for going in Tonga. And I think there's going to be a requirement for us internationally to come together and bring together a lot of deep sea cruisers to go and map and identify and sample some of these volcanoes to look for some further ones along the Marianas, along the Indonesian arc, along Japan arc, and I'll keep naming them. They're all around the world, but the arc ones would be where we'd start.
Any other questions? Well, I think this has been a really, really interesting panel. I've enjoyed it a great deal, hearing from all of you. And I guess maybe Stephanie, sort of final thoughts on kind of what the, where the IMS will go from here, since we're at the CTBTO conference, or kind of any final reflections on how this fits with the mission and the goals of the CTBTO?
Well, I think we are on a good way. I mean, from the technical part and from the data part, there's not much to improve. So, yeah, I think basically we are on a good way.
All right. Well, I am happy to end it there, I think. So I'd like to thank our panelists very much for your time, especially Sarah for doing this on Zoom. Always a challenge. You've performed admirably from afar. Really work that mute button like a pro. So thank you. And thanks to all of you for listening to us.